The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I want to start off by telling you guys some about the reactors that you may or may not have heard of yet in the undergrad curriculum. I know when I was an undergrad, we didn't spend too much time on non-PWR and BWR reactors. So I just wanted to introduce you to them and get you thinking about when you choose your core design, what sort of things do you have to be thinking about? And this isn't just for the core group, this is for everyone, because the choice of the core will help determine the outlet temperature, the amount of power, all sorts of other things that are going to trickle down to the process heat, hydrogen, and biofuels folks. So for those who just walked in, if you need paper handouts, they're up here. If you're fine with electronic, then you're fine with electronic. So some of the main parameters to consider, this is not an exhaustive list, is what sort of coolant do you want to use? There are pluses and minuses to each coolant. What kind of moderator do you want to use? Is the coolant the moderator? Are the coolant and moderator different? What sort of thermodynamic cycle do you want to use? For example, if you're using a gas, do you want to use a Brayton cycle? If you have a phase change material like water, would you want to use a Rankine cycle? What are your inlet and outlet temperatures? The outlet temperature is going to be pretty important because that's going to tell the process heat folks what they have to work with. And then the process heat folks will tell you what the losses are and tell the hydrogen and biofuels people what they have to work with. What neutron spectrum is it going to be? Is it going to be fast, thermal, epithermal? There's always materials concerns, and I'm actually a materials scientist as well as a nuclear engineer, so I'll be weighing in pretty heavily on that. What's the power density? And the power density and the size of a reactor can help you determine the size of the core. Are there any special features, like are any of the designs you're looking at have a positive void coefficient, in which case I don't think you're allowed to use them in the US? How ready is it to make a commercial reactor? And this doesn't mean, can you build one tomorrow? This means, do you think with some certainty that in the next 5, 10, 15 years, there'll be a licensable design that you can manufacture? Because if you're going to come up and say, oh, I have this great design, it works perfectly from the physics, I don't think the licensing will be there for 100 years. Nobody's going to listen to you in your lifetime unless you come up with some pretty major updates and changes. What sort of safety systems does it have? Are they active or passive? Are they both? If the actives fail, can passives take over? And then you have to start thinking a little bit about what happens in an accident scenario. What's the efficiency? And I want to stress the efficiency a little bit. You might not want to necessarily go for the max efficiency, because you're not just making electricity in this class. The goal is to make electricity and hydrogen and biofuels and use them in whatever way you guys decide. So the most thermal to electric efficient reactor might not be the one you guys necessarily choose. And then finally, what sort of fuel do you want to use? And there are more considerations, but especially now that we cut a half an hour off class, I don't want to talk about every single one. Just some relative scales for the parameters I'll be going through. As far as outlet temperature, when I say low, I mean something below 400 C, since a lot of the light water reactors have outlet temperatures in the 320 range Celsius. So we would consider that low temperature process heat. A medium temperature reactor, there's some more materials concerns to think about. So we're talking here 400 to 700 C. The heat coming out can be a higher temperature, which allows you more flexibility in terms of what you want to do with it when it comes out of the reactor. And the high temperature ones, over 700 C, very high quality process heat, and it starts to open up the playing field for a lot of different hydrogen production processes, like the sulfur iodine process, in terms of making it efficient enough to make it worth it. As far as the power levels, if you remember from the constraints on this problem, I don't want you guys to design a reactor that's less than 100 megawatts electric, and that's just to make sure you're dealing with a large system, that there's the right number of zeros on your design. So these are just what I'm calling low, medium, high for the following slides. And in terms of feasibility, I would say something would have a low feasibility if, let's say, there's been a test reactor. maybe it didn't go so well, or maybe it was in a submarine and sank to the bottom of the ocean. Medium feasibility, I'd say there are some operated plants, some designs, but it's not really a widespread thing. High feasibility would be something like a BWR, a PWR, a can-do reactor, something that's been a pretty successful program in not necessarily the US. So welcome to the world of acronyms. Do any of you guys know about the CASTLE project, the Consortium for Advanced Simulation of Light Water Acronyms, reactors? We have more acronyms than English words. I recently compiled a list of acronyms for this project, and it spans 4-page double-column table. Get used to it. There's going to be a lot of acronyms, and as long as you define them at the start of any presentation or report, you can just use them like English words. So, does anybody recognize a lot of these? Yeah? What about the NNFR? Does anyone know what that is? That's the natural fission reactor. There was a site in Africa, I think at Oklo, where there was enough uranium ore and water to moderate it that fission reactions just spontaneously begun and stopped, and begun and stopped with a cycle of 100,000 or a few 100,000 years. It was a long time ago, but you can tell from the fission products in that ore that fission reactions took place. But I wouldn't consider that for a design. There's only one place to do it. So just to start with one genre of gas-cooled reactors, with some more acronyms for you. When I say NU, I mean natural uranium, and LMH here stands for low, medium, high enriched uranium. Anything that is over 20% is considered high enriched uranium. And I believe, anyone correct me if I'm wrong, that we're not going to be able to use high enriched uranium after a certain time. So you may want to consider that when you're thinking of which core to use. I'm not going to put actual numbers on this because I don't think it's necessary. So has anyone seen this one before, the Advanced Gas Reactor? Just raise your hand if you've heard of it before. Okay, so you've heard of it. This is sort of a mainstay in England. This is the next generation of the Magnox reactors. It's gas-cooled. It's quite big, and you can see it has a fairly low power density. Looking at this reactor, if the coolant is a gas, let's say CO2, the moderator here is graphite. Why do you think it would have a low power density? Or how could you tell just by looking at it that it would probably have a low power density? Yeah?
Low density, but wouldn't you need water to the same amount of heat?
You certainly do. You need a high flow rate to remove that amount of heat. And there's the coolant and the moderator are separate. The point is it just takes up a lot of space. And in addition, this graphite oxidizes in very hot CO2. So you have to have systems in there to cool the graphite. So there's a lot of stuff in the reactor, and the core is not as tight as some of the other cores, like liquid metal cores. Let's see. It has a fairly high outlet temperature in the 640 to 650 Celsius range. And it's pretty feasible. Like I said, this is sort of a mainstay in England. It's kind of interesting. Part of the reason they use AGRs in England is a political reason. It was supposed to be the British homegrown alternative to the American light water reactors or the Canadian can-do reactors. And it's not without its design flaws. But this was pushed pretty heavily through the political route as well as the design route. So some of the special features of the advanced gas reactor, it's capable of on-load refueling, or at least part load, which means you don't have to shut the reactor down to reload fuel. You can do this continuously, or because of some derating problems that the reactors have had, you can ramp down to about 50% power, and then you can refuel, which means that you don't have a complete outage unless you have a planned shutdown or an accident or something. So that's a plus. But one of the minuses is, like I said, the graphite moderator has to be cooled because it can oxidize in hot CO2. So the pebble bed modular reactor, this is sort of a favorite of some of the folks in the department. Have you guys heard of this one? Did any of you ever meet Professor Kadak? Yeah, he was sort of championing this design. It's pretty cool. It uses helium as a coolant. It can potentially have a very high outlet temperature. And it uses somewhere between low and medium enriched uranium, depending on the design. It's a graphite moderator, and I'll get a little bit to that a little more of that in a second. It's a fairly low to medium power level. The M, as you see, stands for modular. So some of these things are supposed to be designed to be 10 to 30 megawatt plants that fit on the train car and you can transport somewhere. There are designs being considered that are bigger, which is why it's on the map here. You know, it's not like I'm giving you a 10 megawatt reactor and saying don't choose this. It's just for fun. The feasibility, I'd say, is low to medium. There are some smaller plants being constructed. South Africa has recently decided to stop funding for the program, is what I've recently read. But I think China's going ahead with it. So we'll see in the coming years, and pretty shortly, whether or not this design takes off. The fuel for the pebble bed is not what you would recognize from a light water reactor. There are these what's called triso fuel spheres that are about 6 centimeters in diameter. And inside those are hundreds of thousands of tiny little kernels, these coated particles, less than a millimeter in diameter, that have an outer and inner layer of some pyrolytic graphite. It's kind of porous. The inner stuff helps absorb the fission products. There's a layer of, right now, silicon carbide, which acts as the barrier to, one, keep everything inside the pellet from getting out, and two, that's sort of the stress holding layer. When you have a whole pile of these pebbles, all the stress from these pebbles, which can be a lot, is going to be resting on some of those bottom ones, and that has to hold up that stress. Luckily, it's a sphere, which is the best designed to hold up against stress from all directions. And inside is a little kernel of uranium dioxide. So some of the pluses for this is it's a continuous fuel cycle if you do it right. As you can see down here, there's a pellet discharge tube. Rather than shutting down the reactor and dumping all the pellets, pellets are continuously fed in and dumped out, where they can be checked to see if they've reached the correct burn-up. If they have burned up, they can be discarded or disposed, and they're already in a nice little ball. All you have to do is put them in something else safe and store it. And if they're still ready to go, you dump it back in the top. So, as I said, it's Pebble Fuel. The pebbles act as a built-in disposal method. They're being designed with very passive safety systems. So the folks that are designing these are saying, if everything goes wrong, you can cool it by natural circulation. There won't be any heat up problems or anything like that. There are some unknowns. For example, can the pebbles actually hold up against the stress of all the pebbles on top of them? And can they do it at the beginning of life? Can they do it at the end of life after everything has been highly irradiated? And there are a lot of materials concerns. For example, when uranium undergoes fission, it produces most of the elements. Some of these actually attack silicon carbide. Palladium in particular is one that I studied for my UROP. It turns out palladium can attack silicon carbide and form intermetallic phases, which are either brittle or liquid at pebble bed temperatures. They're thinking of using zirconium carbide as an alternative, and the testing that we've done shows that it fares up pretty well. But we haven't been able to find 100% dense zirconium carbide anywhere. And every time I see someone's paper and they show some zirconium carbide and it's 100% dense, I'm like, oh, can I get a sample of that? And they say no. So I don't know. It's either proprietary or who knows what. And then there's the very high temperature reactor. It runs at a very high temperature. They've been saying 1,000, 1,100 degrees Celsius. That may have to be downgraded a little bit, 950, 900. If you guys look at the history of designs claiming VHTR parameters, the outlet temperatures are sort of creeping down, because not a lot of metals can hold up pretty well in terms of corrosion, in terms of just holding up their own weight at 1,100 C. It uses low to medium enriched uranium. You can either cool it with helium or molten salts. I've seen both of these designs. It's a graphite moderator, and there's some similar features to a pebble bed. You can still have some of those kernels that are either in spheres or they're encased in these what's called prismatic blocks, these hexagonal prisms of graphite with these particles inside them. It'll be a fairly low power level, at least the designs I've seen. The power density changes depending on which coolant you're using. And this, you can see in this diagram, actually, they've drawn it with a hydrogen production plant. Don't let that bias you and just be like, well, that's the answer to hydrogen. This is certainly the answer to hydrogen if you want to use a hydrogen production process at 1,000 C or 800 C. But there are other ways to make hydrogen. Let's see. So some of the special features, this is the highest outlet temperature that we've seen in terms of all these designs. It's the highest one that I'll show you. And so it opens up all the doors to the highest quality process heat, which is one of the things you guys are going to want to make, but not the only one, so keep that in mind. There are significant materials concerns when you go to this high temperature. And any perusal of the Journal of Nuclear Materials, you'll find 100 papers on that, maybe more. Some of them from here. Molten salt can be corrosive in some ways obvious. Let's say you have a chloride salt or a fluoride salt, and there are some insidious ways, which I'll actually get to in another reactor design. The nice thing is it's a single-phase coolant, so unless you have some real bad stuff happening, you're not going to boil that molten salt. And helium's already a gas, so coolant voiding is almost a non-issue. And there are the ups and downs, like I said, to using these triso-fuel particles. So on to some water-cooled reactors. And like I said, we're not going to go through PWRs or BWRs or any variant of those designs, because that's outside the scope of this course. One acronym is, when I say D2O, I mean deuterium oxide, which is also known as heavy water. The CANDU reactor, so this is sort of the mainstay in Canada. It uses a D2O coolant. It has a separate D2O moderator. I can just point this out. The coolant is in these tubes right here, which are called calandria tubes. This is actually the pressure boundary in the CANDU reactor. This moderator right here is unpressurized. It's also not heated directly. The calandria tubes are actually thermally insulated. So having that nice cool moderator as a giant heat sink is a nice safety system. And another cool thing about this, you can see there's a fueling machine here. The CANDU is another design that you can fuel while it's running. You can just pull one rod out, put another rod in, and as long as there hasn't been any mechanical deformation for any reason, usually goes pretty smoothly. It can use natural uranium as well as low-enriched uranium. Does anyone have any idea why you wouldn't necessarily have to enrich the uranium in a CANDU reactor? Keep in mind it has to do a lot with the coolant and the moderator. Just shout it out if you have an idea. Yeah?
It doesn't move that many neutrons from the neutron life cycle because D2O doesn't like absorbing neutrons.
Yes. H2O, otherwise known as dihydrogen monoxide, is very good at moderating neutrons. It's also fairly good at absorbing them and forming D2O. D2O's capture cross-section for neutrons is not as high. So in some configurations, at a slightly lower power density, you can actually run this with natural uranium. Now, there are pluses and minuses to using natural uranium. The obvious plus is you don't have to enrich it. You get it from the ore, you make natural UO2, and you use it. Why would folks think it's bad to use natural uranium? Does anyone have any ideas? Yeah?
You create more plutonium?
You can, yep, you have more U-238, so you can create more plutonium, but in order to do so, someone needs to know you have it. It's a lot easier to get natural uranium than enriched uranium. You don't need an enrichment plant, and the safeguards aren't as severe. So people are saying there is a proliferation risk to having natural uranium reactors because it's easier to get your hands on. And like you said, you can still make plutonium with it. So if you choose the CANDU reactor, I would address the proliferation concern, whatever way you guys want, I don't know. And this is a high feasibility reactor. These are used widely throughout Canada and India. It's kind of an interesting note. Canada and India, up until the mid-70s or so, were pretty good friends, and they shared some nuclear secrets. And then in 1970-something, I think it was 73, India conducted its first atomic bomb test. And Canada was like, we're not friends anymore. And India was like, that's okay, because we have your designs. And there's at least 13 CANDU reactors in India based off of the Canadian design. Even though they weren't cooperating, they figured it out anyway. So a lot of these major design choices tend to happen for political reasons. For example, does anybody know why carrots are orange? Not the chemical reason, but carrots used to come in like white, yellow, red, orange, purple. Why don't you see them anymore except at Whole Foods?
Wasn't it? It was in Holland, and orange is their national color, so
Yes.
they bred the orange carrots only.
Absolutely, it's a political reason. There was also a duke or a prince or something, Sir William of Orange, and to pay tribute to him, they started breeding orange carrots, and it caught on, and that's why you don't tend to see fancy. Well, now what they call fancy carrots, they're actually like regular carrots, except at fancy restaurants. So a lot of the things around you are here for strictly political reasons. It's kind of strange. The AGR is like that. The CANDU in India is like that. You'd be surprised. So this is what one of these calandria tubes looks like. The fuel bundle's on the inside. There's a pressure tube, and there's a spacer with an inert-ish gas in the middle that acts as an insulator. So it can be immersed in this D2O moderator without heating it up too much. All the heat's pushed out by the gas to the steam generator. Let's see. Oh, the moderator is expensive. If you want to make an actual CANDU reactor, expect to drop about $1.5 billion in D2O. Unlike light water reactors, where the coolant and moderator is not a significant fraction of the cost, the moderator here is about 25% of the capital cost of this plant. Now that can be offset by nice things like on-load refueling and other safety features of the CANDU, but keep in mind, if you want to convince someone to build a CANDU reactor, they have to be willing to write you a large check. It's also nice that the moderator, as I said, is unpressurized and thermally insulated. The RBMK, I'm sure I won't say this right, the Reactor Bolshoi Moshnosti. Does anyone know Russian? No? Thank you very much. I think I'm originally Russian like 100 or 110 years ago, but it's all been lost. Do you know what that means, by the way? High-powered channel type reactor. This reactor, well, if you guess by the name, what's the most famous RBMK you can think of? Chernobyl, right. Now, they're not all that unsafe, and by the way, Chernobyl would mainly happen because of a lack of understanding of the physics in the reactor and operator idiocy. It uses water as a coolant. It has a fairly low outlet temperature because it uses water as a coolant. And as you can see, it's got a steam generator of some sort in here. It can use low-enriched uranium, or it can also use natural uranium. It's graphite moderated. And what does the graphite moderator have to do with the RBMK and what happened in Chernobyl? Does anybody know? Yeah?
Caught fire.
It certainly burned. But before that, how did it help initiate it? It does. This design, as it was, has a positive reactivity coefficient. You increase the temperature, the reactivity goes up rather than down. That's bad news, to the point where it was like, I think it was more than 0.7 beta or something. Very high. The control rods were also tipped with graphite, so as soon as you insert them, there's an initial spike in power before it starts to come back down. That's also bad news when you have an accident that only takes 4 seconds to increase in power 600-fold. They can be pretty high power. We're talking 4 digits up in the 1,500 megawatt electric design. There are still some of them running, actually. They have a fairly low power density. And I say the feasibility is medium because it's been done, but there are safety concerns. And you will probably have a hard time convincing anyone in this country, let's build RBMKs, because there's that stigma with them. This is actually a photo of the reactor hall in Chernobyl 3, one of the units that did not have the accident. It is possible to refuel online. These tubes here, a crane can come down, pull one of these tubes out, pop in a fresh one while it's running. So that's another plus of it. We already went over the high positive void coefficient. There have been improvements in design. There's no more graphite-tipped control rods. There are more control rods. And they've had to do a little bit of power downgrades and other things to make sure that the reactivity coefficient is still positive, but it's smaller, so it's more controllable. But like I said, good luck convincing someone in the US, let's build a whole fleet of these. And the supercritical water reactor. When you look at the diagram for this, what's the first thing you notice? Yeah?
The primary circuit goes directly to a turbine.
Yep. So it's a one circuit kind of thing. It's a very simple design. That's a plus in terms of building it, in terms of complexity. Uses supercritical water as a coolant, and as a result, it can get to higher temperatures than plain old light water reactors. Does anyone not know what supercritical water is? Just raise your hand. Or, yeah, okay. I will get to that on the next slide. Supercritical water is when you reach a certain temperature and pressure, the line between vapor and liquid goes away. Steam, liquid, same thing. It's a fairly high density compared to the gas, lower density than the liquid, but there's no distinction between the phases anymore. It uses supercritical water as the moderator, and they can have a fairly high power level and high density. Right now, the feasibility is low. There have not been, as far as I know, nobody's built one of these gigantic supercritical water reactors for now. But this is one of the technologies that the Department of Energy is looking at as a Generation 4 reactor. So just for reference, I put up the phase diagram for water here. A lot of other materials have supercritical points like CO2. There are designs that have been proposed with supercritical CO2, but there are some corrosion problems there. So I just put water up for now. At 374 C and 22.1 MPa, there's no real line between solid and liquid, and we just call it supercritical water. It's a very simple design. There are significant materials concerns, and there are some folks here that are working on materials corrosion in supercritical water. Coolant moderator voiding is pretty much a non-issue because you can't boil something that acts like a gas. It's already a gas. It can get less dense, but you can't form giant voids in it. They run at a pretty high efficiency, so we're talking upwards of 45% is what's being claimed. Now, there are startup procedures. In order for a supercritical water reactor to be running, the water has to be supercritical, and things don't often start out at 374 C and 22.1 MPa. So there can be some instability issues when starting up a reactor whose coolant is not the same as it is at room temperature. But it is theoretically possible. So on to the liquid metal cooled reactors. These are some of my favorites, probably because I studied lead bismuth eutectic for my PhD. And there are also, there's one acronym I want to get into. We used to say NAC, which stands for NAK, sodium potassium alloy. It's actually liquid at room temperature. I think the freezing point was like minus 11 C or something. So on to the SFR, the sodium fast reactor, or you could do a sodium potassium fast reactor. When you look at the diagram for this reactor, what's the first thing you notice that's different from a lot of the other ones we've seen? Yeah?
This is pool type?
It's not actually considered a pool type. There is a big pool, but this is considered a loop type. You can't pump water as a secondary coolant into a pool full of sodium. I know I don't have to ask this, but have any of you guys ever seen sodium explode in a river? Okay. Yeah, you wouldn't want to pump sodium directly into the pool. You can have a secondary circuit, which could also be sodium, but you wouldn't want to be pumping water into activated sodium. So you need a secondary loop to get the heat out, depending on the coolant you use. Uses liquid sodium or NAC as a coolant. Right now, proposing a pretty medium output temperature, but Tyrell, I think you were saying there's a new design being proposed.
Yeah.
What is that?
It's something in Russia. They're trying to pump out 1,800 megawatts of electric. And
Wow.
the outlet temperature is supposed to be a little bit higher than what we thought was possible. I don't know the exact number.
Okay, that would be interesting to consider. I'd probably put that in the low feasibility though, since it's a paper reactor right now, right?
Yeah.
Okay. It can use natural uranium. Oh, sorry, it can use, that might be a typo. That should be an M, not an N. Sorry. So it can use either medium or high enriched uranium. There are designs that can go over 20%, but I wouldn't recommend it for your class. Doesn't have a moderator. This is a fast reactor. Sodium moderates a little bit, but not very much. You can design them to run at all power levels. They can go anywhere from little plants like EBR in Idaho to this monster Russian thing that's being proposed right now. They have a pretty high power density, and I would put the feasibility as low, coming up on medium. There are a few sodium reactors right now. There's Monju in Japan, Super Phoenix in France. There was one of the EBRs in Idaho. Actually, I've got a pretty cool picture. This is liquid sodium at Monju. I found this on a website of a French guy that went to visit it. And you can actually see if, I'm sure most of you have seen sodium in its solid or exploding form, but not necessarily in its liquid form. So this is what it looks like. It's kind of cool. You don't need to pressurize it. Sodium just needs an inert cover gas, but you don't have to pressurize this reactor, which has some pretty obvious safety implications, like how can you have a loss of pressure accident when you don't have pressure? Sodium has a very high thermal conductivity, pretty good heat capacity, so it's great at pulling heat out of things, and it's highly compatible with many materials. So sodium doesn't necessarily corrode things like stainless steel, which is great. There's a high boiling margin. Sodium boils just shy of 900 degrees Celsius. And if you're running this thing with an outlet temperature of 500, 550, even 600 C, you have a big margin to go before you can actually boil any coolant. There are concerns to worker dose. Sodium can activate with neutrons. It has fairly short-lived isotopes, but there is a concern to people working there. And there's this concern to people working there. I actually have a little story. A couple years ago, I went to visit some labs in Belgium, the SCK-CEN lab. And they have a sodium reactor mock-up loop. It's not a reactor. It has a heater. And there are sodium pipes running throughout the building. At some point, I asked, where's the bathroom? And the people looked around and they just started snickering to each other a little bit. And they say, don't you remember your chemistry? There's no plumbing in this building. There's no sprinklers. There's no toilets. And then they pointed around the room and they said, you see those buckets of sand everywhere? And all of a sudden, I was like, oh yeah, there's like 100 buckets of sand in this big room. And they said, if there's a fire of any kind, you take as much sand as you can and you cover that fire in sand. And if you run out of sand and you do not run out of fire, you run out of the building. So don't let that dissuade you from picking sodium as a design. This was a test loop, but that's when I just thought to myself, like, oh yeah, I wasn't really thinking about all the safety implications here. And then there's the LFR, the lead-fast reactor, or the LBEFR, can't really reach, the lead-bismuth eutectic fast reactor. Does anyone not know what a eutectic alloy is? So eutectic alloy is the lowest melting point combination of two or more other metals. So for example, lead melts at 330 Celsius, bismuth melts at something. You put them together in about a 45 to 55 ratio, and it brings the melting point down at 100 to 123 Celsius. That has some obvious positive implications. If you have a reactor that you want the coolant to be molten, and it's normally solid, you don't have to heat lead-bismuth eutectic as much to melt the coolant and get things flowing as compared to lead. There are minuses, though. Bismuth can form, I believe bismuth forms polonium under neutron activation. And bismuth is also a lot more corrosive to materials. It's about solubilities for things like nickel and chromium are 10 times higher in bismuth than they are in lead. And I'll just say, if anyone has any questions about lead bismuth anything, you can ask me, because I've done nothing but study that for 5 years in terms of materials and where it would go in a reactor. You can also talk to Professor Bongiorno, who for part of his thesis designed a lead bismuth design where you bubble steam directly through the molten metal. It's kind of a wacky design, but very interesting. I'd also put the feasibility here at low bordering on medium, because we're making some advances now in terms of the materials. I'm just plugging my own research, or in terms of other designs. There have been a few of these plants. For example, the Alpha-class submarines from the Soviet Union used lead-bismuth reactors to power them. They unfortunately ended up running these reactors like a toilet, and I'll explain that in a second. In order to control corrosion in lead or lead-bismuth, you have to do one of two things. One, you have to make sure there's absolutely no oxygen in your system, or that the materials can passivate and it doesn't matter if there's very little oxygen. Or two, you run your system at the lead oxide or bismuth oxide potential. So there's an equilibrium between lead oxide and bismuth oxide. Problem is, if you have chunks of lead oxide flowing through your reactor, they can clog the pipes, and then the submarine can sink. And some of them did. It's funny, a lot of these Alpha-class subs, if you look online, they weren't in service for more than a year or two. They were pretty much designed to be fast attack subs to intimidate us. I don't believe they were ever used to sink anything. But this way they could say, oh yeah, we can chase down any of your ships with these things, and sort of another political move, which is the reason these subs became into existence. Lead has a pretty high heat capacity. It's not quite as good in terms of heat transfer as sodium, but it doesn't have that whole exploding problem. It's self-shielding. Lead is a pretty good gamma shield. You have to melt the coolant first. For sodium, it's not as much of a problem because the melting point's around 80 C, 90 C. For NaC, sodium potassium, it's already liquid at room temperature. For lead bismuth, it's 123 C. For lead, it's 330 C. There's essentially no possibility of avoiding the coolant. Lead bismuth eutectic boils at 1670 Celsius. So you'd have to have a really bad day to get any of this to start boiling. You do create polonium, and that is fairly long-lived. If any of you guys remember that Russian spy that had some bad sushi, that was polonium that did him in. And there are significant materials corrosion concerns. And lead bismuth is expensive, especially the bismuth. There's not a lot of it. Bismuth costs something like 6 or 8 times as much as lead. We don't have nearly as much of it. So that's a concern. Whether you're designing one reactor or whether you're designing a fleet of reactors, take into account the price of bismuth because it might surprise you. And the last reactor I'll get into is the molten salt reactor, which some folks are saying is the most probable of the so-called Generation 4, or the revolutionary reactor designs being considered by the Department of Energy. Do you guys know about the Generation 1, 2, 3, 3+, and 4 reactors? Where Generation 1 was, guess it, the first. We're currently on about Generation 3 or 3+. Those are considered evolutionary designs. Generation 4 reactors are revolutionary designs. Rather than just improving on an old design, you start from scratch, do something crazy like this. When I say FLIBE, I mean lithium and beryllium fluoride salts, just so you know, but everyone just refers to it as FLIBE. The molten salt reactor can use FLIBE and maybe a combination of uranium or thorium fluoride salts. So the coolant can be the fuel. So you can actually be pumping fuel through the reactor. That has some pluses in terms of simplicity and such. It has some minuses that you have to continuously clean up your coolant fuel in a chemical processing plant because you have to remove the fission products, some of which are poisons. It has a medium to high outlet temperature. It can use usually medium enriched uranium. It has a graphite moderator. You can design them to be at all power levels. Has a very high power density. And because the DOE is touting this one on top, I'd say the feasibility is medium. And just to sort of put it into perspective, this is FLIBE. I didn't know what to think of when someone said molten salt until I found this picture, and it's just looks like a regular liquid, except it's really hot. Again, with the molten salt reactor, just like the lead bismuth, the lead and the sodium reactors, you don't need to pressurize the core because it stays a single-phase liquid coolant. You can put thorium and uranium salts to be used as the fuel and the coolant. It has a very negative temperature coefficient, which is good for safety. But remember when I was saying that molten salts can be directly corrosive and corrosive in an insidious way? A high neutron flux can transmute lithium and produce tritium. Tritium on its own has to be collected, or you have to make sure that it doesn't get out and get to anybody. But tritium, which acts chemically just like hydrogen, can combine with all the fluorine in these FLIBE salts and make HF, hydrofluoric acid. Have any of you dealt with hydrofluoric acid before? No? It is the worst stuff in the world. There's a special antidote called calcium gluconate. If you get HF on your skin, you pretty much have to flood the area with calcium and try and get the fluorine atoms to make calcium fluoride with the gluconate gel before it starts to pull it out of your bloodstream. And by the way, calcium regulates your heartbeat, it's in your bones, and it's really bad stuff. It's also really bad for a lot of metals. HF is one of the few materials that can dissolve quartz. And we use it in our lab to dissolve the quartz off the silicon carbide when we really want to know what sort of corrosion is going to happen in those trisofuel particles from the Pebble bed reactor. And it does require on-site salt reprocessing. So some of the questions that if I were in the core group I would ask myself would be, which coolant do you want to use? What implications does that have all the way down the line for this design? what outlet temperature do you want? Because depending on what coolant you use, you may have a range of outlet temperatures, or you might be pegged in a certain small range. How big of a reactor do you want? The size of the reactor is going to have a pretty big impact on the biofuels people mostly, because if you make a 100 megawatt versus a 1,000 megawatt reactor, you don't take up that much more footprint. But if you're dealing with 10 times more biofuels, you have to have 10 times more land. And you could go from something where you grow crops in a couple miles around the reactor to where you have to have local distribution centers bringing in biomass to your plant. So the core folks, keep the biofuels folks in mind when you're choosing the size of your reactor. Is it going to have primary, secondary, tertiary cycles? What are the heat exchangers going to look like? What are the implications there? Will it have a recuperator, as in will the hot and cold streams pass by each other to help raise the inlet temperature, for example? So let's say you had a very high temperature reactor with an outlet temperature of 1,000 degrees. You don't necessarily want to bring back in 100 C gas, because having a huge temperature gradient can have some pretty bad thermal expansion stress effects. Lots of other bad things could happen. How much electricity versus how much process heat do you want? So you guys together are going to have to balance how much electricity, how much process heat, and when the process heat is made, how much goes to hydrogen, how much goes to biofuels. Can you come up with any other products that you could make with the rest of this process heat? For example, when you were making biofuels, you could end up with some charred straw or some random biomass that you can't turn into anything. Could you package that, sell it as house insulation, and make some more money for almost no investment? And where in the cycle should the process heat exit? Do you want to take it off the top when it's the hottest and then send it back through the turbine? Or do you want to put it through the turbine and then take it off the bottom of the cycle when the heat is fairly cool? And that'll depend a lot on the hydrogen and biofuels production processes that you guys choose to use. Something else I'd like you guys to do by Wednesday's class is come up with a group contract. I'm not going to tell you what to say, but I want you guys to put in it what you promise each other, because only 30% of your grade in this class is dependent on your work alone. The other 70 is dependent on the class as a whole, but the biggest fraction is dependent on your sub-team. So I'd like you guys to think about, what do you want to promise each other to make sure that you all perform well? Do you want to promise to be on time to meetings or only 5 minutes late? Do you want to promise to split up work equally? Do you want to promise to play to strengths or give people different things to do that they've never seen before? Do you want to open every meeting with a joke? Do you promise to meet at the Asgard or suitably fun location? That's where my team met when I did this class, so that's not out of the question for you over 21 folks. And I would like the subtask leaders, whoever you decide to be, to give your contracts to the integrators, to either Sarah or Catherine. Have everyone in the group sign and date it. Keep copies for yourself and give a couple copies to them so I can keep them. Because I don't want to be the one putting pressure on every single one of you guys. I'd rather make you guys do it. Plus, it means more coming from you. So in these next few minutes, pick who wants to be the leader. I'd say separate according to group and choose who wants to be the subtask leader.